the next slide, we're looking into that flange in a little bit more detail. So you can see, basically, it's kind of a T, right? So you have, I can change my pen over here. So if you look at the cross section, basically that's that cross section that's kind of like a T-bar that gets breaked off. So on that flange of that T-bar, basically on the left, you have 2 rows of rivets or screw holes that screw the panel screwed on, and the right is essentially the same thing. So if you zoom into here, you can see the crack actually probably, you can see some marks over here, right? You can see this mark and that mark. So that's where you want to do your post-mortem analysis to try to find out what's going on. So this is in the report, which it shows there are 3 stages of fracture or of crack propagation. So the red mark is the fatigue side, and then at some point the crack has a static jump. So that's most likely when you have an upload or a large load, the crack propagated, but then it stopped because of some mechanism that actually arrested the crack. And then you continue with some fatigue loading, and then eventually it broke. So that's basically the story of that part. So you can look into more detail if you zoom into the flange. So that's where they identify the crack initiation started at this point, which is where the flange is connected to the panel, and you can kind of see the crack propagation, right? So you see the marks over here, the crack is propagate in that direction. So on the left side, it reached the end of the flange, and of course there's nothing there. And if you actually did inspection, you will probably see it. But unfortunately, this is kind of inside a box. It's not that easy to inspect. Maybe now they have some robot arm to go in there to inspect that. So this was in the 70s, so they didn't do any of those things. So it was not detected, and then the crack on the right-hand side started to basically fatigue and propagate toward the main body of that flange. You can tell from, I think over here, you can tell that's where crack initiated, because what they see is on this panel over here. That's the panel that attached to it. There were lots of fretting, so basically there were lots of rubbing. So supposing if you have a very tight bolt, the shear should not have much of rattling or movement, so you shouldn't see fretting. But in this case, it see the fretting, so that means this bolt over here is not, this bolt over here is not really very tight, so that's probably an indication of crack initiation. And then they also show in here, you can see where the hole in the back gets elongated. So essentially the load gets passed on and kind of stretch on that. So those are the indication when they do investigation, they can identify those abnormalities and then decide that that's where the crack initiation. So now you can see why, like when they have a crash, of course, the first thing they want to is locate the black box, because that's what things get recorded. But they also definitely want to find all the parts so that we can put it together and identify where the potential cause for this problem accident. So let's look at now. This basically is visual inspection, and probably lots of experience coming into here. So now the next step is now, based on this information, maybe you can do some static or stress analysis or mechanics analysis to see whether basically kind of validate what you see in the crack surface. So as we said before, we have basic crack initiated at this point, right? And then you have fatigue crack growth up to that point. So in this case, this airplane actually was operated by Pan Am until then. So the crack actually already quite large crack, but was not detected, and then they either get acquired or get sold to Down Air. So the Down Air essentially inherited airplane that already have quite lots of fatigue damage. So when it's reached here, there's a static jump that the crack propagates very quickly from here to there. Okay. And then the crack gets arrested again, and went through a bunch of fatigue cycle, but also have some, like over here, you can see some small static jump, and then eventually it had the minor static jump, and then eventually it has another static jump that's probably right before it crashed. So it had that jump, and somehow it gets arrested for a very short period of time, and then eventually the whole thing breaks. So that's how the whole history of the crack propagation through that surface. So what we're going to do now, next step is, first we will analyze at what condition this crack propagated, has this static jump, and then we will do the analysis on what caused this surface, this crack to arrest, and then we'll go from here. So based on what you have learned so far, how would you approach this problem? Keep in mind that this is 1970s, so we don't have a lot of facility for finite element calculation. Finite element really picked up in the 80s. Before that, not many people have finite element method for simulation. So let's focus on this guy first, right? So what kind of crack that look like? And if I go back a little bit more, just putting a better picture of. Right, so this is the part look like, right? So it's a long box extended all the way to the wing of the airplane, and then the cross cut, section cut is like that. So now we're going to focus the first part, which is just at the corner of that T. So if you want to, obviously, we need to find out the stress intensity factor for this crack. What would be a geometry you can simplify this problem into a simple geometry that you could have some way or have a design curve or some way to calculate this stress intensity factor.
A bar with through hole.
A bar with a through hole?
Yeah.
Where is the through hole?
In the knot, where there is a thread for the knot.
Okay, so let's see. So this is a T, right? Does this part matters for your calculation? And when your crack front is over here, right? Does that part have a big effect on your stress intensity factor, you think?
There's a hole in between, right?
There's a hole, that's the screw hole over here, or rivet hole over here. And that part is completely broke off, right? Not broke off, but it's completely, so when the crack reach where I draw, this part is completely through, right? So it's not connected to the other side at all. So do you think this part will have an effect on?
Probably not.
Probably not, right? So it's because this is so far away from that front, so we can probably just take that out and assume we have a free surface over here. Okay? All right. How about this end? Yes? No? Okay, so let me ask a question. So in this case, you have a crack front, and do you think the stress intensity factor will be the same along this edge or not? Not stress, yeah, the stress intensity factor, do you think will be the same?
No. The closer to the boundary, there will be boundary effect.
Okay.
There will be-
And over here, maybe not, right? Okay. So the effect of these, so in this case, which way you think is more critical? Which point is more critical along the surface?
The upper one?
The upper one over here?
Yeah.
Okay. Why do you think?
More stress, maybe?
Why do you think it's? How is this stress? Where does the stress come from in this case? Which direction is the stress actually? Right, so if we go back and see how the that's the bar we're talking about. This guy over here, right? And it's so if I draw, right? Okay. Okay. So this is the bar. This is, let me call this y direction, right? and that is where it's attached to the airplane. And so in this case, that's where it's attached to the airplane. So this direction is the y direction that I draw there. Okay. So where does the stress come from in this case? Or where is the dominant stress direction? Did you guys watch the videos the last time? So if you have the wing stand out this way, this is my
Tension at the top.
right. So if you have your arm stick out, so my arm direction will be my y direction, right? That bolt over there is my shoulder. Okay. So if I hand weight on my wrist, I will have bending. And then if you feel it, that this will have tension. That depends on, for the airplane, of course, you also have lift, right? So that's where the fatigue cycle comes from, is that bending stress. So that means you have essentially, in this case, you have sigma yy pulling it, right? That's how it breaks, or the stress that causes the damage. So in this case, that means the stress is pulling out, right? So you have tension over here, and then maybe over here. So that's how it's get bent. Because this right now I'm zooming in. This is the portion, top portion of it. So you can, if you look over here, right? So assume your neutral axis is at the center over here. Then these are so far away from the neutral axis that you can pretty much make a reasonable assumption that the stress over here are similar, right, or relatively uniform. So then the break over here and the break over here, which one is more critical? So when you look at that, you look at how much material you have left, right? So in this case, from here to here, you have pretty big, thick material. But from here to there, this side, first of all, this side again have the rivet, so that will have a force moving on that. Because that gets passed on through the rivet here. And then if you look at the material over here and the material over here, clearly that one has more material than that material, that section. So I would think this side has smaller K than this side. Does that make sense? Okay. Okay. So we could, if we want to consider, so this one probably more critical, and then this is less critical because they have more material over here. Obviously, if we cut over here, right, if we don't consider that, this will introduce an edge effect, right? So we'll essentially make this higher than what actually is experienced. So which is okay. You just want to have a rough estimation. So now we know that the left, we don't need to worry about the right. We will take it out. Keep in mind that that might overestimate the K. How about the bottom? Can I chop it like this? If I chop it like this, will this have a large effect that I chop off? Have a large effect on the calculation over here? No opinion? Probably not, right? Because it's so far away from where I am now. So this is my cracked front. So most likely this will not have much effect. So I'm just going to chop it over here. And so that basically, if I take that, so what I have is, this is my cross section. I have a bar, and I have a fracture surface like that. And then my load is coming in and out, right? So that's the first approximation of this problem, is where you assume that you chop off all the things that are not critical for you, and trying to find the simple geometry that is similar to what you have. And then we'll show it later. Then you of course you keep that in mind, and later you need to compensate for that. Okay. So once you have this, and now it's basically we are looking at the cross section. This thing extends far away, right? So we can treat it as a bar with this kind of 45 at a corner with a crack. So these are the dimensions we can see in this case, that the crack for the first static jump, the crack is almost kind of a quarter circle, is 31 millimeter. And then for the second one, it's not as, for the second one, it's not as nice, but you can just approximate it as it's a semi or quarter circle, and then take an average of that. It's 41 millimeter. The total length from here to there is 75 millimeters. Okay. So basically that's where we start. So now, once you simplify that into a bar with certain length, so in this case it's a rectangular bar, and so you go back to the handbook and to see if you have some graph that will help you determine the stress intensity factor or not. In this case, now of course it's easier. Now you could take that and do finite element calculation and find what the stress intensity factor would be. But at that time, it's mostly depends on experimentally calibrated curves. So in this case, he can only find a problem which is a bar, has an edge crack like this, and with the stress going along the length of the bar. So that's similar to what this top chord look like. So it gives the K0 and all that, and then in this case is looking at the angle from 0 to 45. Obviously this is symmetric, so that point is the same as that point. So if you calculate the other, it's the same. So you can see that starts from the center line, which is 45 degrees over here. That's not very good 45, but take it as a 45, right? So as the angle gets smaller, basically as you move toward the edge, this gets bigger and bigger. The K1 over K0 gets bigger, and then eventually it reaches 1.28 at the edge. So of course going the other way toward the other surface is the same. The only thing in this case is that the cross section of the bar is rectangular, it's a square, so it's, the length and the width are the same, and also the crack length is only 0.2, it's 20% of the overall length, right? So if we go back to here, we have this guy with that guy. So there are two deviations from what that table showed, that graph showed. One is your cross section is rectangular. The second thing is the crack length is much larger. In terms of ratio, is about 50% of the width instead of 20%. So how to comment? So in order to use this, obviously you need to compensate for those differences. So how they compensate is use edge crack to account for the surface. So in this case, he has again a chart that's showing for an edge crack, if you have load applied. So in this case, the crack will be a through thickness crack. And how the length versus the width of the plate will have the effect, right? And in this case, they have also two cases. One is whether the bending is unconstrained, that means the plate can bend. Another case is when the bending is restrained, so that you can only go up, not tilting, basically. And obviously for this case, do you think the bending is constrained or unconstrained? So we go back to what we have, the operation condition of this plate. Is it restrained or unrestrained?
Restrained by the top?
It's restrained by the top surface, right? So most likely, if you look over here, okay. So in this case, if the bending is unconstrained, that means I have this surface, I can bend like that, okay? But in this case, I have this top plate over here that prevents it from bending, right? So in this case, we have an unrestrained case. So we're going to use that curve. We're going to use that curve, and that curve, what that curve gives you is the effect of the crack length versus the boundary. Okay, so okay. So let's switch to the board, to my paper. So we have analysis of the first static. Okay. Then we have, so the cross section, as I said, is rectangular. This is 46 millimeter. And then I have a crack length of 31 millimeters. So the reference is true. One is we have a square bar. And at that surface, I have a graph like that. So basically, that's kind of approximate what I'm seeing over here. So in this case, I have a square, and then that's A over here. So that's the equation give me. So based on that, I have my K at the corner is 1.28 times 2 theta square root of A over I. So that's from the book, from the table we have. So to compensate for all this edge effect and the crack length, so this is for A, if I call this B. Okay, so I cannot use this directly. What I will do is to use the data from edge crack. And again, I have B. So in this case, so the K, if you remember, is you have this edge effect times K0. I call that K nominal. So in this case, the K nominal is that one. So at A over B equal to 0.2, based on the table I'm showing over here. So 0.2 is over here, right? So I have, it's about 1.2. And then I need to find out, in this case, what will be my, in this case, what will be my B? So I actually have two cases, because I could say A over B over here, or I could say A over B over here, right? Because depends on which way you look at it. So for the actual case, right, I have that A. For the core problem we have in hand, we could A over B is equal to 31 over 46, or I could have A over B equal to 31 over 75, right? So in this case, what can I do? I just take the average of these, okay? So I will have and that will give me about 0.5. From that, of course, you can find the y of 0.5 based on that graph is 1.45. And so what that tells me is my result over here is based on A over B equal to 0.2, which based on this, have a boundary effect of 1.2. But in the actual case, I have A over B equal to 0.5, so I have a boundary effect of 1.45. Okay, so what I will do is I take this and factor that in. So my K1 is going to be equal to, so I call this the square or calibrated, will be equal to y of 0.5 divided by 2 times. So that gives you 1C, which is okay. So that's how you can basically combine these two and then make a reasonable estimation of how you can calculate the K1, because this is the first step we need, otherwise we will not be able to go any further. So from here, now the next step is, of course, we already know A is 31 millimeters, so we just need the stress, what would be the stress. And in that case, have to go back to Boeing to find out what would be the maximum stress under the condition they have. So based on that, so Boeing basically did a calculation, finite element calculation on just how the stress gets built up over here, and then they find out at that condition the stress is probably somewhere around here. It's 13 something, I think, based on that, and then it's the stress was but it's a 15 KSI somewhere over here. So based on that, then you can plug that in. So this is definitely a stress plot is important. Okay, so from the static analysis or stress analysis, the sigma is equal to 15 KSI, which is 103 megapascal. So if you plug in all those into that number, so you find K1 is equal to, you plug all those in, so it's 1.45 times. And what you get is 31.56. Okay, so what is this value? What does this value indicate? That value is the stress when the crack, or the stress intensity factor when the crack is at this location. So what does it say about that stress? Is that the stress intensity factor something special, or why do we interested to find out the stress intensity factor at that point? Right, because that's when the crack have that static jump, right? When the crack has a static jump, that means the critical stress intensity factor has exceeded, right? So you can, based on the behavior of the crack, okay, you can say that this actually is my K1C. So because that's the stress intensity factor right before the crack make the jump. And for so the aluminum material, and they have a 7079 T6, and based on the material data sheet, the K1C is between 30 to 35 megapascal per square millimeter. So this definitely is within the range of that. So that gives them confidence that even though they have done some approximations, but that gets very close within the range. So that's how, in case you find that this number is much lower, either you have to go back to look at your calculation, or you have to find out whether the material has some problem, right? So now, because this is within that range, you can see that they are actually, the crack is behaved like what it's supposed to be. Okay, so the next question is, why does the crack why does the crack will propagate and but then stop?
Introduction.
Right. So the question is, why is that the crack didn't propagate and just continue propagating and break the part at that time? If it did, then that will be Pan M's problem, not Daniel's problem. But unfortunately, maybe good luck for Pan M, that it didn't break the part. And so Daniel ended up with the problem. So what could be the mechanism you think that make the crack stop, arrest, the crack gets arrested? What's that? Right, so if we go back to look at here, what resisted the crack from breaking apart?
Is it because of the top?
Right, because the top, actually, the top skin is still holding the two parts, right? So if you look at, so it doesn't have a good picture. Right, if you look over here, so right now the crack is still somewhere over here, and so the top still have that skin. So even though the crack jumped, and as the load comes down, the skin will take more load, and then they will hold the crack into place, and then that's why it didn't completely break. So the next step, obviously, so to answer that question is we need to do a calculation to see how much the load gets basically supported by the skin. Remember, they changed the skin, right? They had aluminum skin before. They changed it to stainless steel because they want more rigidity, and the steel probably is more is stronger also to take load. So that caused the problem, but in one way also kind of postponed the accident. Okay, so let's go to. Okay, so then we will do the analysis. Okay, so so if I draw the part, so this is my chord. Let's say it's actually wrong. And I have a crack goes like that. And the thing is, if it's like this, it's going to crack is going to propagate and fracture the whole thing. But in this case, you actually have a skin on top of it. So that's what is holding up. So if I look from this side, what I see is I have a bar and I have a crack. Of course, I'm exaggerating the crack. And then on top, I have the skin that's holding it up. Okay? So if my crack wants to propagate over here as you load it, that some load gets transferred over there. So the stress intensity will be a combination of this stress and the loading over there. So if I take the skin out, so I do my free body diagram. Right. So I have my stress, and I also have the shear, I call it P, from the skin, because in this case, I removed the skin, so I replaced the skin with the shear force that the skin has. So both this and that, based on the superposition, will give me the actual K effect on that, and then we can calculate from that. Okay. So in this case, we have back to here. So we want to calculate the arrest, for which is this line over here. And obviously they are not very well behaved as a quarter circle as what we have expect. So we just take the average of those two and then use the crack length of 41 millimeter for our calculation. So we have A average is equal to 41 millimeter. And for this problem, we have the solution K1 is equal to 2.6 P without the stress, of course, the base over pi A. Okay, and so for the stress, so K1 due to the stress we had before, we were just using the edge crack. We're using the edge crack equation. So in that case, my y A over B is equal to y of 41 over 75. I'm taking the long one. So that gives you 0.5y. And from that, you get, this is 1.5 from the table, the graph I have. So my K1 due to sigma is equal to what you get is and so K from the K1 from P is equal to 2.6 times P. At this point, I don't know the P yet. The B is, let me just write this. B is 46 millimeter. So, well, I leave it for now since I don't know P yet. So my actual K actually is K1, then is the stress plus K1P. So for the, so how do I find the P over here? Obviously, right now I don't know P, and what that stress needed to be for the crack to arrest. What's that K1, the stress you need? Should be less than K1C, right? And we already found K1C from the previous analysis. So from here, and then that is equal to 71.5C. And so from that, we could calculate PS is equal to, it's actually minus. So what does that mean?
It's just in the opposite direction.
Right. So we will assume it as a tension, and so that means the stress is in the opposite direction. So the skin is trying to hold it back, right? So the skin is trying to hold it back, while the part is, or the outside stress trying to open it. So at that point, the skin was strong enough to hold it so that the part did not fall apart completely. Okay, so what that means is we need to take into the skin into consideration at the final fracture. So we need to take the skin function into consideration because now we know that the skin serves some kind of crack arresting effect. So let's consider okay. So now when we need to consider skin, if we go back, if we go back to here, you can see that the left have the skin and then the right. So basically those are the skins kind of holding on this side and that side. And that's what it holds back. So we're going to just approximate it as if, so this is the cross section we see, and then we're going to approximate as it has just the skin that covers all along it. So the approximation would be, if I look at the cross section, I have my P bar, go a little bit lower. This is my skin over here, and then my T-bar. It's like that. So that's my screw hole over here. So the crack propagates start this way and get to the point where. So that's the crack propagation. Okay, so in this case, we know that the skin thickness is 1.25 millimeter, and that the flange thickness is 12 millimeter. Okay, my joint is not to the proportion to what it actually is. So in this case, we have left and the right. We will assume the strain on the left is the same as the strain on the right. And so we essentially have a composite material here. We have two material. This one is steel, and that is aluminum. So to calculate the material on top, we will use the Young's modulus of composite material. And which is the rule of mixture. So that's essentially you calculate your effective Young's modulus is based on the components you have. So the equation is the effective Young's modulus is sigma I T I. This one should go over here. Okay, so and we also know that for in this case, my steel Young's modulus is about 3 times my aluminum Young's modulus. So on the right hand side, the part is intact, right? It's not broken yet. So that's where we're going to apply this rule. So ER will be equal to, by applying that, basically is my steel times T steel plus aluminum times T of the flange over. So you plug in that, your effective Young's modulus is just about 20% higher than aluminum because of the steel, the skin that you have. So on the left side, what will be the effective Young's modulus of the left side when the crack is over here?
Same as aluminum?
Same as aluminum?
Steel.
Same as steel, right? Because the bottom is already broken off.
Okay.
Right, so it's just the skin is taken. So the left side is equal to because the flange is broken. Okay, so from that, we can calculate what is the load take by the left, will be the stress times to the left, which is only the skin. And since we assume the strain is the same, so we have the steel times epsilon L times the length of the cord, which doesn't matter, times T of S. The right, of course, is the same, except the material is different. So you have effective times epsilon L times L. The right and left is the same, times TS plus TF. So you still have both of them there. So the ratio between these two, now I can plug that in, will be equal to all these cancel out, just the thickness. So that gave me so essentially, the left side only have 24% of the right side because now the flange is breaking off. We know that the total load to hold the part is 150 kilonewtons. So P from the left to the right, we find that it's 150 kilonewtons. So from that we can calculate PL is 29 kilonewton and the PR is equal to, you can find that. But in this case, obviously the left is the most critical one. So we can find the stress on the left is PL over A, and so that is why, because this did not break the skin per se, because this stress actually is much smaller than what actually it has. They also did the calculation on the bolts over here. So basically, you have, if you look at the bolt, then that's E is equal to 6 millimeter. So you have essentially the skin is pulling on, right? So you have P left on that. So, but usually how the bolt break will be, it gets sheared over here. So if you do a free body diagram, then it would be that PL over the tau that shear the bolt. So in this case, the fastener is essentially P over pi r squared, and you plug in the number. Good. So that's another reason that, so the bolt didn't fall off either, because this load, the stress was smaller. So it was not sufficient to shear the bolt or to tear the skin off. So that's why it didn't break those parts that you can see. And the only thing that caused the problem was it broke the whole flange and caused the airplane to crash. So, okay, well, I actually finished earlier. I was trying to finish that so we don't need to come back on Thursday. Okay, I think that's kind of give you an idea of how you use this material that we teach in class to do some basic hand calculation to kind of understand how this works. This really differentiates a good engineer from a bad engineer in a sense, because the problem you will run into at work if you happen to need to use the principle of fracture mechanics, it's most likely not something that you can find in the book. But hopefully this kind of give you an idea of how you can use what you learned from the class to solve a real life problem.